Good morning, dear students. My name is Ferhan Mazher, and today is 13th March 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. Today, we have set our hearts to solve a theory paper. We call it paper 2, and we have selected October November 2015 2 paper. This paper belongs from the zone 2, or you can say it belongs from the variant 2. In this session, we are going to solve the section B of this paper. The section A of this paper we have already solved, and I have already uploaded in my YouTube channel. So today we are going to attempt the section B of this paper. So let's start and open that paper. Okay, so this is the section B. This is starting from the question number 9. Aeroplanes fly at high altitude where the temperature is well below 0 degrees centigrade. Ice that forms on an aeroplane can fall to earth and strike the ground. Figure 9.1 shows a block of ice falling from an aeroplane as it approaches an airport. So this is that piece of the ice which is falling from this aeroplane. The mass of the falling block of ice is 1.2 kg, and the gravitational field strength G is 10 Newton per kg. The question is, calculate the weight of the block of the ice. I can calculate the weight of this. The formula for the weight is W equals to mg. The mass must be taken in kg. So here we go. Let me show you. Okay. So let me go to the question number 9. Sorry for this inconvenience. Okay. So W is equals to mg. So 1.2 multiplied 10, and that will be 12 Newton. So our answer is 12 Newton. So let's check the marking scheme. 12 Newton is the right answer, sir. The figure 9.2 is the speed time graph for the block of ice as it falls to the ground. So as the ice is falling at the start of this observation, when the time is 0, the speed of the ice is also 0, and the speed is accelerating. And then at here, somewhere here, like 7 seconds, the speed becomes constant. It's called terminal velocity. And here it had hit the ground. At 11 seconds, it has hit the ground, and the ice has hit the ground. So its velocity all of a sudden from 40 becomes 0 at 11th second. So this is at first the acceleration of the block of ice is equals to the acceleration of the free fall. The acceleration of the block of ice is equals to the small g, which is 10 meter per second square. The acceleration of the block then decreases to 0 as the block reaches terminal velocity. At terminal velocity, the acceleration becomes 0. The speed of the falling block will become constant. We call it terminal velocity. As the block of ice falls, the force F of air resistance acting on the block changes. State the value of the F at time equals to 0. So you see, when the time is 0, when the time is 0, you see the speed of the block of ice falling downward is 0. So because there is no speed of, it's not moving, its speed is 0. So the air resistance F will be also 0. The air resistance depends upon the speed of the body. If the speed is 0, the air resistance will also be 0. So I will put here 0 Newton. Then he says state the value of the F at the time equals to 10 seconds. So when the time is 10 seconds, here you can see the velocity of the falling ice cube has become 40 and is constant. And when the speed is constant, it means terminal velocity. It means that the downward and the upward force has balanced each other. It means that the air resistance is equals to the weight of the body. And you know, weight is 12 Newton, so the air resistance will also be 10 Newton. Then he says explain why the F changes. So why the F changes? because the F, the air resistance, depends upon the speed of the falling object, and because the speed is gradually increasing, so the air resistance is also increases. So when the speed will become constant, the air resistance will also become constant. So let me show you my written answer. So the state of value of the F at time equals 0, Newton. State the value of the F at the time 10 seconds, that will be 12 Newton. Explain why the F changes. Air resistance F depends on the speed. As speed is increasing, F increases. When the speed becomes constant, F air resistance will also become constant. So that's the answer. So let's have a look at the marking scheme carefully. Okay, so here is a marking scheme. He says 12 Newton as it is equals to the weight. F increases as the speed increases. And the first answer was 0. Okay, so our answers are right. So next question, second part. He says state the energy changes that take place when the block is falling at the terminal velocity. Remember, whenever an object is falling at a constant speed, we never use the word kinetic energy. So when the block is falling at the terminal velocity, when the block is falling at the terminal velocity, its gravitational potential energy will be converting into the thermal energy. We will not use the word kinetic energy because the ice is falling at a constant speed. So the gravitational potential energy is converting into the thermal energy or the heat energy. So then he says, using the information from the figure 9.2, determine the maximum kinetic energy of the block when it is falling to the ground with the terminal velocity. So from this figure, I can tell the maximum velocity is 40, and we can calculate the kinetic energy. The formula for the kinetic energy is, it stays formula for the kinetic energy is 1 by 2 mv square. So here is your solution. Gravitational potential energy converts into thermal energy. Kinetic energy is equals to 1 by 2 mv square. So 1 by 2 into 1.2 kg into 40 meter per second square. So you get 960 joules. 960 joules is the right answer, sir. So let's have a look at the marking scheme. Okay, so our answers are right. Okay. Here, this word is kinetic energy of the air. Okay. So 1 by 2 mv square, so 960. Okay, so then what's the question? He says, the block strikes the ground and it stops moving. This impact causes some of the ice to melt. The specific latent heat of fusion of the ice is 330 joules per gram. Calculate the maximum possible mass of the ice that melts as a result of the impact. The heat is equals to ml when the state changes. So we know the value of the heat, we know the value of the L, the latent heat, and we can find out the M value. So heat is equals to ml, 960 joules, and M is question 330 joules per gram. So M will be 960 divided by 330, and the answer will be 2.9 grams. 2.9 gram of the ice will be converted. And let's have a look at the marking scheme. What the marking scheme says. Okay, so the marking scheme says 2.9 gram. Okay, so our answers are right. Okay, he says in practice, the mass of ice that melts on impact is less than the value calculated in the first part. So there's two reasons for this. You see, we have supposed that when the ice hits the ground, all the energy is converted into the energy which is you converted in this kinetic energy is used to melt the ice. But you see, it's possible that the ice might be colder than the 0 degree centigrade. The temperature of the ice might be less than 0 degree centigrade. In that case, some of the energy will be used to first of all raise the temperature. For example, the temperature of the ice is minus 5 degrees centigrade. So some of the heat will be first used to raise the temperature of the ice from -5 degrees centigrade to 0 degrees centigrade, and then the ice, the energy will be used to melt the ice. So the one reason that the mass of the ice which actually melts is less than the mass which we just calculated, the reason can be that the temperature of the ice might be less than 0 degrees centigrade. Another reason can be that when the ice hits the ground, some of its energy, some of its kinetic energy is converted, is used to produce a depression on the ground. So some energy used there, some of its energy might be used to produce the sound when it banged into the earth. So that sound is also requires energy. So not all the energy used to melt the ice. So let me show you my written answer. So here we go. So the temperature of the ice, I forgot to write here the word ice. The temperature of the, where's that word? Ice. Here we have to write the word ice. The temperature of the ice. The temperature of the ice might be below 0 degrees centigrade. Some energy lost to create depression on the ground. So that is the our answers. Okay, let's have a look at the marking scheme. Some. He says any two forms. The ice is below 0 degrees centigrade, or the thermal energy transferred lost to the ground and air. Work done compressing or compacting the ground. Okay, so that's the marking scheme. Then the next question, and it's the D part of the question number 9. As the solid ice melts, it changes into liquid water. Describe in terms of molecule how ice differs from the liquid water. You see, in the ice, the molecules are in a regular pattern on a lattice, and in the ice, the molecules remain in their fixed positions, and they only vibrate about their fixed positions. And the molecules, the intermolecular spacing in the ice is larger as compared to the intermolecular spacing of the molecules of the water. You see, the behavior of the water is little different from other liquids. When you convert the water into ice, the its volume increases. That's why we are use the last property, in which we are saying that the distance between the molecules of the ice are larger than the distance between the molecules of the water. So let me check and let me show you my answer. In ice, molecules vibrate about their fixed positions. On a lattice, molecules are arranged in regular pattern. Molecular spaces are larger in ice. Okay, so let's have a look at the marking scheme. Okay, so the any three from the molecules fixed in position, or water molecules move around, molecules vibrate or water molecules do not vibrate, molecules in regular lattice or water molecules placed randomly, interatomic forces between ice molecules larger, ice molecules further apart. So you have to write 3 points from here. So that was question number 9. So I hope you understand this. Okay. So we are going to the next question. He says, okay. Thin wire covered in plastic insulation is used to make a solenoid, long coil. The solenoid is connected to a sensitive ammeter. Figure 10.1 shows the north pole of a steel magnet placed next to the solenoid. Point X and point Y are on the axis of the solenoid. Explain why plastic is an insulator. You see, the plastic is an insulator because the plastic does not have free electrons in it. Because it does not have free electrons, so the charged particles cannot move through the plastic body. So that's why the plastic is an insulator. So let's have a look at the first answer. Plastic do not have free electrons, so the charges cannot flow through plastic. So then the next question coming up is explain why the magnet is not made from aluminum and it's not made from iron. We do not make magnets. Sorry, I said plastic. Explain why the magnet is not made from aluminum. Aluminum is not used to make magnets. The reason is very simple, because the aluminum is not a magnetic material. And why we do not use iron? Because iron is a soft magnetic material. When something is soft magnetic material, it do not retain magnetic properties for a long time. So that's why we don't use iron to make magnets. So let me show you my written answer. Here we go. It is for aluminum, we'll say it is a non-magnetic material, and for iron it is a soft magnetic material. Soft magnetic material means it do not retain its magnetic properties for a long time. So let's have a look at the marking scheme. Okay, so question number 10. No free electrons in plastic, or electrons are bound structural. Aluminum is not magnetic, cannot be magnetized. Iron is a temporary soft magnetic material, or is not a permanent magnet. Okay, so that was question number 10A part. So question number 10, its B part. He says in one experiment, the magnet in the figure 10.1 is moved to the left and passes into the solenoid. The north pole of the magnet travels from Y to X at a constant speed. As it moves, the ammeter shows a small current. Explain why there is a current in the solenoid when the magnet is moving. So 3 marks question. You see, when you will move this magnet towards the left and it will move from Y to X, the magnet is moving, the steel magnet is moving relatively to the coil. So when the magnet is moving relatively to the coil, its magnetic flux passing through the coil will change. Due to the changing magnetic flux passing through the coil, an EMF is induced in the coil, and the current will start flowing in the coil. It's a 3 marks question. So let me show you my written answer, and then we will have a look at the marking scheme. Due to relative motion of the steel magnet and the coil, magnetic flux passing through the coil changes. Due to changing magnetic flux, EMF is induced in the coil, and that's why the current is induced in that coil. So let's have a look at the marking scheme. The marking scheme, the magnetic flux mentioned, the magnetic field lines, cut wire, solenoid, circuit or changing magnetic field or flux, voltage, EMF induced. So these are the 3 marks. Our answers are perfect. Okay, so next question. He says the North Pole travels Y to X in 0.14 seconds. As it moves, the current shown on the ammeter is 0.045 milliampere. The resistance of the solenoid is 1.2 ohm. Calculate the potential difference across the solenoid. You know the potential difference V is equals to IR. We know the current, that's 0.045 milliampere, and the resistance is 1.2 ohm. So very easily I can calculate the potential difference. So V equals to IR. So 0.045 expo minus 3 multiply 1.2, because we do not take the current in milliamperes in this formula. We take the current in amperes. So that's why I wrote here expo minus 3. 0.045 expo minus 3 multiply 1.2. That will give you 5.4 expo minus 5 volts. So 5.4 expo minus 5 volts. So that is our answer. So let's have a look at the marking scheme, what the marking scheme has to say. 5.4 expo minus 5 volt, that is the right answer, sir. Okay. Then he says the charge that passes through the solenoid as the north pole moves from Y to X. I know the current. I know the current flowing. I know the time taken. So very easily I can find the charge. The formula is I is equals to Q divided by T. If you want to find out the value of the charge or the Q value, the formula will become I times T. So 0.045 expo minus 3 multiplies 0.14 seconds. So you get 6.3 expo minus 6 coulombs. So that is the amount of charge which is flowing. And let's move to the next part. Okay, so let's have a look at the marking scheme. He says okay, we're done with this. So what is the question? We know the time. So the final answer is 6.3 expo minus 6 coulombs. And that's this answer. Then he says, in a second experiment, the speed of the North Pole is greater than its speed in the first experiment. It now takes 0.070 seconds to travel from Y to X. You can understand that before it took 0.14 seconds, now it is taking 0.07 seconds, which means that it is now taking half the time. It means the magnet is moving faster. It means that the speed of the magnet has become double. That's why it's taking the half time. So he says, state and explain, and the current in the same direction is shown on the ammeter. State and explain how the size of the current compares with the size of the current in the first experiment, because this time you are moving the magnet faster. You have doubled the speed of the magnet, and so the current produced also will be doubled. So let me show you my answer. So the speed of the steel magnet has doubled, so the change in the magnetic flux will double, so the current induced will also double. That's our answer. So let's have a look at the marking scheme. If it is larger or twice the current, magnetic field lines cut faster and magnetic field changes faster, or twice the current. So that is the answer which is written there, C part, and our answers are right. Then he says the same quantity of charge passes through the coil in both the first and the second experiment. If you look at the formula for the charge, you know, charge is equals to uh, the formula. The charge is the product of the current and the time. You see, in the second case, the time it has become half, but the current has become double. So when you multiply them, you will get the same amount of the charge. So charge is the product of the current and the time. In and the time, I have to write here and the time. Okay, charge is the product of the current and time. When current doubled, time becomes half. So the charge is constant because you double the current, but you have made the time half. So that's why the charge will be okay. Double the current of or half the time, a larger current for less time produced. I multiply T is the same. Okay. So the next question. State two ways in which the equipment shown in the figure 10.1 can be used to produce a current in the solenoid that is in the opposite direction. You see, if you want to produce the current produced right now in opposite direction, so there can be two things. Either you change the polarity of this, reverse the polarity of this magnet. Here you have the north pole, just bring south pole here and north pole there. The direction of the current here will change. Another method can be keep the magnet like this, but now move it towards the right side. So this north will move away from the right end of this solenoid. So the current produced will have an opposite direction. So let me read my answers. Reverse the polarity of the steel magnet, or you can move the steel magnet towards right. So these are the two methods. So let's have a look at the marking scheme. Any two from the insert south at the same and insert north at other end. Withdraw north pole from the same end employed. Withdraw south pole from the other end or pass through completely. Okay, so our answers are right. So question number 11 is coming up on your screen. It says the proton number, atomic number of the element lead is 82. The isotope lead 209 is 82209 is radioactive and decay by the emission of a beta particle. Describe the composition and the structure of a neutral atom of the lead 209. You see, the neutral atom will have 82 protons in its nucleus, and it will have, I think, one. You just subtract them, the mass number. 82 protons and 127 neutrons in its nucleus, 82 electrons in its orbit. So that's the structure of a neutral atom. And let's have a look at the marking scheme. Okay, 127 neutrons, 82 protons, and 82 electrons. Electrons in orbit around the nucleus, in shells around nucleus, or around neutrons and protons, or neutrons and protons in the nucleus. Okay, so now we are moving to the next part, and the next part is this part. That was a 3 marks question, simple and straightforward question. A nucleus of the lead 209 emits a beta particle. State how the composition of the nucleus produced differs from the original nucleus. You see, whenever a beta particle is given out, the daughter nucleus has one proton number more, so its proton number increases by one, and its nucleon number do not change. So it means that because the proton number has increased, the neutron number will decrease by one. So let me show you my written answer. Whenever a beta particle is given out, the number of neutrons decreases by one, the number of protons increases by one, and the mass number do not change. So the nucleus produced will have 83 protons, 126 neutrons, and the nucleon number will be 209. Okay. Then he says in the next part, he says, let's have a look at the marking scheme first of all. Okay, so you can read this marking scheme carefully. Okay. Complete the table figure 11.1 to show the relative ionizing effect of the 3 types of ionizing radiation produced by radioactive. The least strong ionizing is the gamma rays, then we have the beta, and the most strong are alpha particles. So gamma, beta, and alpha. So our answers are right. You can see at the marking, look at the marking scheme. A sample containing lead 209 nuclei is used to produce a beam of beta particles. The beta particles enter a magnetic field. The magnetic field is perpendicular to the direction of the travel of the beta particles. The beta particles travel from left to right. Show figure 11.2 shows that the direction of the magnetic field is out of the page. On the figure 11.2, sketch the path of the beta particles in the magnetic field. So let me switch on my camera and let me show you how this is done. So I will use the left hand rule to find out. So here I'm going to apply the left hand rule. So let me change the, okay, so here you can see this is my left hand. I will stretch my fingers like this, F, M, C. So it's F means the force, M means the magnetic field, and this middle finger shows the current. So the current is going like this, and you know it's towards me. You can say like this. You see, it's like the magnetic field is towards me. It's out of the page. The charge particles, they are going from left to right. My thumb is pointing towards the bottom of the screen, but the beta particles are negatively charged. So it means that the beta particles will be deflected opposite to what the left hand rule is predicting. Because the beta particles are negatively charged, the beta particles, they are negatively charged, and the law is not about the negative charges, it is about the positive charges. So whatever the direction my left hand rule is telling me, I will make I will the beta particles will be bended opposite to that direction. So by using the left hand rule, I can tell you that the beam of beta particles will be deflected towards the top of the screen. So that's the how you will write that, how you will do that. Okay. So let's have a look at the marking scheme. Circular by curve from beginning of the field, not with the straight line initially, upward curve in the field. So our answer is right. Okay, so we are moving to the next part, and that's the C part. He says an industrial technician uses a detector to measure the background count rate in a laboratory. State what is meant by background radiation. You see, the background radiation is the radiation which is all the time present around us without any known sample of the radioactive material around us. The radiation which is all the time present around us and our bodies, our plants, our animals, they are used to that radiation. That radiation is called background radiation. So let me read the answer for you. Here we go. Radiation present around us without any source is called background radiation. Um, yeah, to some extent, yes. Radiation that is always present or occurs everywhere cannot be eliminated or from environment surrounding natural sources, air. Okay, so our answers are right. Okay, the next question is, suggest two major sources of the background radiation. And the radiation is one source is the cosmic rays, the radiation which is coming from the outer space into the onto the earth or into the earth. So that's the cosmic rays. That's the one source, and the other source can be, there might be some minerals in the soil. So in that locality, so which is causing the background radiation, there can be many reasons. Okay. So two separate sources, for example, rocks, for example, radon and ground, outer space, for example, cosmic rays, man-made sources, for example, nuclear waste or nuclear fallout. So that is our answer. I hope you can note down this answer. Okay. So let's move to the next question. He says, the average reading for the background count measured by the technician is 16 counts per minute. He then brings a sample that contains a radioactive isotope of lead close to the detector, and he finds that the new count rate is 92 counts per minute. The half-life of this isotope is 3.3 hours. Determine the count rate measured using the detector after 6.6 hours. So you see what I will do. From the reading, I will subtract the background first of all from 92 minus 16, and that will give you 76. So when the two half lives will pass, if after first half life, the 76 will become half, so you're left with 38. And when the second half life has passed, the 38 will become half and it will become 90. Now, what will be the reading? The reading will be the reading due to the pure sample plus the background. So the reading on the instrument will be 35. So that was the question number 11, and it's C, third part. So let's have a look at the marking scheme. He says, uh, two half lives employed, 1/4 seen, or 76 counts per minute, 19, 23 counts, and 35 counts per minute is the last and the final answer. So, my dear students, I think that the paper is over. And okay, so my dear students, today we have done October, November 2015 2 paper. We have done the section B of this paper in this video. The section A of this paper we have already done, and its video is already uploaded in the YouTube channel. My dear students, if you find this video interesting, informative, and helpful for practicing Cambridge O levels past papers, do share the link of this video onto your Facebook accounts, onto your Instagram accounts, and onto your Twitter accounts, because that will help me to promote my channel. So I am very proud and I'm very happy that I am to some help to you. So keep studying from my YouTube channel. and the success will come in your way. So may God bless you. Have a good day, and God bless you all.